Thanks very much, Adolfo, and thank you to the organizers for inviting me to speak about our research. Firstly, you can hear me okay, right? Yeah, excellent. Great. So yeah, this session will be about quantum thermodynamics and also open quantum systems. So this is quite a mixed conference. So please interrupt me if you think that I'm losing you, because we hear quite different subjects. I would like to make it interactive, but if you don't interrupt me, I'll just simply go on. So yeah, my name is Janet Enders. I'm a proper quantum physicist. I share my time between two places, which is Exeter in the UK and Potsdam in Germany, and that's what it's like for the moment being. I'm going to talk about work that I've done with a couple of people, quite a few people. Here's a couple of references, and yeah, here we go. So let me start with a very brief introduction of what this talk is basically about. It's about what happens when you have a quantum system, but it's not like in quantum computing when everything is unitary, but we're dealing with actually real systems that are open. So you have damped motion, such as harmonic oscillators that are damped, right? So something interacts with your particle. And the way to properly describe such motion is to consider a system and environment Hamiltonian, so an open system, and discuss that in its full beauty. And there are many, many papers, of course, there's lots of books and everything. And today I'm going to talk about some aspects about this. So let me first start with a very brief introduction to something that you probably have never heard of. You might have heard of the Caldera-Leggett model, which is the standard model for open quantum systems. And in this mini intro, I'm giving you an additional example of an open system that you can solve very well, something that we've done in the group in Exeter. And then I'm going to mostly concentrate on this part here, which is about the steady state of such an open system in something called the mean force Gibbs state, and discuss two limits, the recoupling limit and the ultra-strong coupling limit. So these are going to be some mathematical slides, but hopefully they are insightful. Then I'm going to talk about a second aspect that noise that comes from the environment does to your qubit, for example. It makes it noisy. And the question is, how do you take a noisy high-dimensional state that arises from such a noisy interaction and make it recover a qubit state from it? I think this is a problem that many experimentalists have. So we have some partial solutions. Okay, so let me start with this topic. So one of the things that we've been working on for a while now is really motivated by questions, many questions in magnetism. So in magnetism, people are interested in understanding better how magnetic materials act and work. And to do that, they are currently running, for example, millions of interacting classical spin dynamics. So they solve really millions and millions of these interacting spins to see how a material, for example, with all sorts of impurities and so on, equilibrates in time, for example, and this is really important for many applications, all the way from hard drives to different applications in cars, and all sorts of things. But what they encounter is that, so what they solve is something called the LRG equation. The LRG equation we're going to talk about in a minute again. And this has been working really well. So they've made many predictions that are really useful for industry. They work very closely with industry. But in the more recent past, they have observed for some materials that they're now interested in, some mismatch between the simulations they do. So these are classical simulations, right, of all these atomistic spins interacting with each other, and the experimental findings that you can measure in the lab. So there's a mismatch now that they're interested in understanding. And so, for example, they see that there's a sort of temperature rescaling seems to happen that no one really fully understands. And the question is that due to some quantum effects? So is the difference that they observe between simulation and experiment, has that got something to do with both the fact that the spins are not treated quantum mechanically, but also that the environment may not interact in the same way as they actually currently model in this LRG equation? And so, for example, could there be non-Markovian terms that that also impact on the dynamics? So these are all questions that they can't yet answer. And this is something that we think we can come in because we have quantum expertise. We're less less expertise in magnetism, but we have a lot of quantum expertise. So the question really is, can we help each other? And I'm not going to give you a full picture of everything, and this is not a solved task, but I give you just some outline. So what we've done as a first step is we've derived a generalized LHC equation that's based on an open quantum systems framework, and it can include a quantum thermostat. So it can do this task of including quantum noise, and you can also include memory. This new equation is directly usable in current simulations that they do. So they can simply upgrade their simulation with our code. I'm not actually going to talk about this in all detail, so I'll just give you the outline of it. So of course you need to know what is the LHC equation. So what is it? It's a phenomenological equation that describes the damp dynamics of a spin. So if S is your spin, then the time evolution of it is S cross B, right? That's what you know. But in addition to that, you have also, for example, neighbors with which the spins interact. But then you have two additional terms. So this one here is a stochastic thermal field. And this one here is called a Gilbert damping term. So these are two terms that are phenomenologically included in this LHC equation. And this is what they solve. And what it describes is the precession of the spin and the damping that comes from interacting with an environment. And so what we do is we want to derive that equation, and in fact derive a more general equation. And to do that, we set up a system in Barth Hamiltonian of the form that those of you familiar with the Caldera-Leggett model will find immediately intuitive. If you haven't heard of the Caldera-Leggett model, you won't understand what I'm talking about. Just believe me. So the Hamiltonian for the whole system is the system, this is the spin in the external field, and there is neighboring spin interactions. And then the new thing is that you include also a bath. So standardly you include a harmonic bath with which your spins interact, and you let them interact in such a fashion here. So S interacts with, for example, the position of the harmonic oscillator in the bath. So it looks a little bit like this. So the harmonic oscillators pull on the spin. And here you have a coupling function. That coupling function tells you how strongly each frequency of your bath interacts with your spin. So that's really the setup, fairly standard for some. But what is new is to do that in this three-dimensional case for spins, not what Caldera-Leggett did for harmonic oscillators. And what you find after some algebra is that in the Heisenberg picture, you can actually write down the equation that arises from the spin, from this total Hamiltonian here, and you get this. So you get S time derivative is S cross, here's the external field, here's the neighbor field, and here you have these two terms, okay? Two terms that come, of course, from the coupling between the spin to the environment. So there is first this term, which is a stochastic noise, and secondly, this term, which is a memory term. And they're linked to each other by what is called the fluctuation dissipation relation. And so, okay, without going into very much detail, the point is that you can then recover this LHC equation, the standard equation that everyone uses, under the assumption of a certain linear coupling function. But you can also go beyond it, for example, by choosing a different coupling function. For example, we choose these Lorentzians here. So the main point is you can go beyond the standard LHC equation with a natural systematic way of extending this equation. And moreover, for these Lorentzians, we have a method of solving the dynamics. Again, I'm not explaining this in any detail, but the main thing to understand is that you can numerically simulate such non-Markovian evolution with memory of your spin. But this is a classical spin, okay? Classical spin dynamics, but with full non-Markovian bath and any noise you want, so including quantum noise with 0-point fluctuations. So we can do this very well, and I'm not going to tell you also the details of these slides. The main thing is we can solve the evolution in time. You can see differences depending on whether you use the LHC equation or you use something that is Lorentzian, so you can really see the differences. So we give the magnetism people a tool to explore how you actually modify this LHC equation include also quantum noise. So again, I'm going to skip this. So here are some slides. This is just a plot to show that really they can immediately import what we do in their magnetism simulations. This is just a test plot for 8K spins, so they can immediately test our code and put it in and see the difference when you have many spins interacting with each other. Okay, so this was only the warm-up. So I summarized the warm-up. The summary was based on a system bath Hamiltonian. We've derived a three-dimensional quantum spin dynamics equation that I briefly showed you. And we also use Lorentzian couplings that allow us a systematic exploration of the impact of memory and colored quantum noise on spin equilibration times and steady states. And we have a numerical simulation to do that can immediately import it into current atomistic spin dynamics equations. Yeah.
What have you assumed so far? Because it's still non-Markovian.
Yeah.
Are there any assumptions?
None. It's quite powerful. Yeah. Okay, so what I actually want to talk about today is this topic here. So one of the things that comes out of this is a question about, okay, what does the equation, our spin, right? It relaxes in time. And so these are plots for the steady state as a function of temperature. And maybe we don't always need to solve the dynamics if we have analytical ways of calculating that steady state from the outset, right? That's really what I'm going to ask now. So the steady state, if you have a system and you push it out of equilibrium, you all have learned that the system will equilibrate back to something that we call the equilibrium state. And usually you assume that this is the Gibbs state. Who of you, sorry, I've just taught a blog course with lots of, who of you has heard of the Gibbs state? Okay, most of you, excellent, very good. So most people know that when a system equilibrates, it equilibrates to the Gibbs state, and the Gibbs state is given by a Hamiltonian of the system, and beta is the inverse temperature of the environment. And so that's what we can actually assume our steady state to be, right? But this actually really is true for a system that interacts with the environment, that's a temperature beta or inverse temperature, but interacts really very weakly. What we've just discussed in this warm-up was not that. What we just discussed was this. We discussed that the system actually interacts really strongly with this environment with some V int here and some lambda that gives us the coupling strength. So isn't there a mismatch there? So when we have this environmental coupling, what we should expect to get is that the entire system and environment, will in time equilibrate to the total Gibbs state of system and environment. So that's this guy. And if you're just interested in the system itself, then we take the trace over the bath, right? That's a credible proposition that our equilibrium state should actually be this, and that's called the mean force Gibbs state. And you can check quickly that, of course, when lambda is 0, this state here will become the Gibbs state, of course. That's it. But if lambda is not 0 or approaching 0, then this won't be true anymore. Okay, so the main message really is, are you sure that the standard Gibbs state is your equilibrium state to which your system will relax? I propose it should be the mean force Gibbs state. Okay? Right, so this is not new. People have talked about mean force states for a long time. And for example, this is a slide from Chris Jarzynski, who talks about this in a classical context. And the classical context is always about, small systems that interact strongly with the environment. So for example, biomolecules that interact with the solution in which they swim. These are examples where mean force corrections are crucial. So this is the type of systems we're interested in, and there's a lot of literature on the classical side as well as on the quantum side about mean force Gibbs states. Okay, so back to our question. So the proposal is that a system should equilibrate to this mean force state. And one of the first questions really is, can one actually give this mean force Gibbs state in terms of system operators alone? This is now a mathematical question. So see, the problem is this is a huge dimensional Hamiltonian of the system and a huge dimensional bath. And I'm telling you to take the trace over the bath. Good luck. This is not easy. So the question is, can we give this mean force Gibbs state in terms of the system operators alone? So having already traced out all this bath stuff, what is it? Can we write it down? What are the expectation values of it? And this is where I get to, firstly, the weak coupling limit, which is the sort of more mundane limit. People have talked about it a lot. So if you think about coupling regimes, so here's coupling regimes. So lambda, remember, is our coupling strength. System couples to environment with lambda. And when lambda is 0, then we get back Gibbs state physics, standard thermodynamics or statistical physics. But when lambda is larger, then we are going to enter what I call strong coupling thermodynamics, where these coupling effects really play a role. They change everything, right? They change your partition function. They change how you predict thermodynamic properties of your system. All this will have corrections in it that come from the interaction with the environment. It is not a trivial task. So this is strong coupling thermodynamics. We know that it works abstractly, but now let's be concrete, more concrete. So we are interested in the weak coupling corrections, so to second order in lambda. This is the regime where most master equations arise. So those of you who've studied master equations, you will have always worked in the weak coupling regime, almost always. So what I'm telling you is that one can find a general analytic expression for the quantum mean force state in this regime. So general in the sense of this is the type of Hamiltonian we are looking at. So now I'm talking about this paper here by Jim Kresser, who's really the driving force behind these ideas here. So this is the Hamiltonian that we consider. So some general system Hamiltonian, HS. Then there's the BAF. This is a harmonic oscillator BAF. And then there's the coupling here between the system and the BAF oscillators with some spectral density J. So it's generic in the sense of any system Hamiltonian here. So Caldera-Leggett, spin boson, yes.
Question about Markovian.
Yes. Oh, Markovian comes from the spectral density, and I'm not making any assumption here on what it is. So I'm just saying it's a function of frequency, and depending on what the dependence is, you will have a Markovian evolution or a non-Markovian evolution, but I don't need to specify it just actually at all at this point. Okay, so this is the Hamiltonian. In that sense, it's general. And what I'm telling you is that one can work out what this mean force Gibbs state is. So here's the exponentiated version of this with beta. And then we want to take the trace, and one can now work that out. And the first term, of course, will be the Gibbs state, right? At low coupling, that's what you expect. But then you get corrections to second order in lambda. This is not going to be pretty, right? This is not going to be pretty. This is perturbation theory. It looks like this, okay? So, you get several terms. They all start with lambda square and so on. And there's certain definitions. I can explain all about it. The main thing is, you can write them down. Okay, you can write them down, and they are general. So whatever your system HS is, whatever your this is, whatever your coupling operator is, so that's the coupling operator of your system, whatever that is, you plug that into the definitions of all the terms, presto, you get your mean force Gibbs state. That's the beauty of this. And you also get some conditions of when it applies. So namely, how small does the lambda have to be so that this weak coupling approximation is still valid. Here's an example that I really wanted Timur, who I've never met, to see, because it's one of his papers. They proposed a V system for a certain context. The V system is simply a three-level system. This is the Hamiltonian, and then there is a coupling XS. So this is the coupling operator, remember, that couples you to the BAF. So X couples to the BAF. And this one here basically couples the zero state to a superposition of 1 plus 2. And so what that does is we can work out now this mean force Gibbs state, as I just explained, and then we can start to plot something called coherences. So what actually arises is, and they are not very large because I've plotted them on a scale that doesn't make sense to you just now, but basically there are coherences. So coherences means that if your system Hamiltonian is this way, z direction, your Gibbs state, of course, is aligned with it, and you have no coherences. But because of the mean force corrections, we're going to not align fully. We're going to have coherences in the equilibrium state, and the coherences are shown here, and they actually peak as well. And so that has some implications for all the types of systems that Timo would be interested in. For example, different biological situations, as well as quantum dots, and all sorts of systems are described by Hamiltonians like that. Okay, Another thing on coherences, I'm going to skip that because Timo isn't here, and I'm straight away going to go to the ultra-strong limit. So the ultra-strong limit, as I just discussed, right, we were just talking about the V-coupling limit, but there's also the limit of ultra-strong coupling. So that's the one where lambda is really very large. Okay, that's another limit that you can treat, and you can treat it, well, we treat it. So here again, we want to work out the mean force Gibbs state. I have to use some definitions. So actually, there was a conjectured steady state. Someone, Ryochi Goyal and co-workers, they proposed that the steady state should be of this form. So steady state should be of this form. This is the standard Gibbs state, the tau s, and Pn are the projectors. Pn are the projectors onto the axis, and the axes are the eigenstates of this guy, which is the one that couples to the environment. So the environment is important, and the environment takes this guy and projects it into this basis in which the system couples to the environment. That was the conjectured steady state. That made us very interested in this. And then we proved that actually the quantum ultra-strong mean force Gibbs state is of this form. Looks similar. So here's HS, here's Pn. So, you know, it's very similar. It's just that the Pn's go in the exponent rather than being downstairs, if you see what I mean. So this is what we proved. And they are actually not the same. Okay, they're not the same. And in the papers I really like these papers by Ryochi because they're very clever. What they did is they actually solved the dynamics using something called hierarchical equations of motion to verify that their conjecture is true. And they verified it by solving for a particular, this was the spin boson model. And what you see here are lines. You see solid lines and dashed lines. And the solid lines are ours, and the dashed lines are theirs. So the two states are a little bit different. And you can see that they're almost on top of each other for most times. Actually, for most temperatures, only at low temperatures will the two expressions be different from each other. But they didn't test it at low temperature. Of course, numerically, you have to test it for this specific temperature, and they only tested it at this temperature. And at this temperature, you couldn't tell whether actually it goes to our state or their state. So their statement was true in the sense of their numerics was aligned with what they proposed, but actually our solution is also true. And so by now, it's actually been proven that our state is indeed the steady state of an ultra-strong coupling master equation. So it really is the steady state mathematically, not just numerically. And there's also a numerical method of calculating this state. So if you don't trust our result, you can numerically evaluate the whole trace over the bath and so on numerically, and they produce very nicely our result. So, you know, this is the answer. The answer is it's more complicated than Gibbs state physics. So how much time do I actually have? Yeah. Okay, good. So let me basically show you this picture, which summarizes a little bit the situation. So this is a picture for the spin boson model. So here's a spin. This is the Hamiltonian, but it couples to in the environment with this Z and X combination here. So I've indicated this by this picture here, where this is a Z and X sort of coupling. And what happens is that when you take the standard Gibbs state, you don't see anything of this, right? The standard Gibbs state is only given by HS. And so your expectation value of SZ, which is the alignment with the HS, should be 1. Should be 1 at temperature 0. And you should have no X component. Okay, so that's the gray arrows here. They're pointing at what you standardly expect from standard statistical physics and thermodynamics. The recoupling mean force corrections are the blue line. So that's sort of showing you that you actually start to deviate from this one because of the coupling to the environment. So you see that here and here. And then you can also put in our ultra-strong limit that's here and there. And you see that this line in the middle, that the darker green line here is actually an interpolation interpolates very nicely between the weak coupling limit and the ultrastrong limit, and we've solved that by what is called the reaction coordinate. So this is a numerical method of evaluating this difficult task. So, and it shows very nicely that our analytical solutions give you the endpoints. There's a big question, what are the analytical expressions for the middle? So we have numerical methods, but we haven't got analytical methods at all. So we have only these limits here, this one and that one. And in the middle, it's still very unclear. Okay, so I think you understand. So I've summarized that this mean for skip state is the equilibrium state. We have the analytical solutions in two regimes, and they are for general system Barr Hamiltonians of the Caldera-Leggett spin boson V system type. And we've also discussed a little bit about coherences. In the last 5 minutes or so, I want to talk about something completely different. The link between the two things is simply that the reason of what's going to come up here is also due to the environment. So let me give you a background for that. So a few years ago, I worked with a group in France, Benjamin Huard's group, who did an experiment with superconducting qubits doing a quantum Maxwell demon incarnation. So the quantum Maxwell demon, without going into detail now, is someone who controls the fine workings of, say, a gas or something. But in this case, it's a transmon qubit that's being the transmon qubit is being controlled. So that's inside the cavity, and the cavity itself is like the daemon. So the daemon controls the cavity, extracts work, and so on. That was shown in that experiment. What came also out of this experiment is this picture. This here is the tomography of the daemon's cavity state after the feedback protocol. So what you, for example, what they had was, for example, you want a coherent state. This is in the fog basis. So this is a coherent state in the fog basis. And of course, it's a pure state, so your expected entropy should be 0. And this here is the vacuum state, so there, and the expected entropy is 0, right? And then there were also superposition states, and remember this coherent state is relatively large, so the overlap with 0 is approximately 0. Okay, so basically 0 and alpha are approximately orthogonal, approximately of course. So the entropy either way of this state should be 0. And then you can also have a mixture for which the entropy should be 1. Do you see what I'm talking about? So we're talking about how the cavity can encode photons, photon number, for example, in a vacuum state, in a coherent state, or in a superposition state, or in a mixed state, right? And that's what they do in experiments. Okay, but so this is what the tomography shows us. And what it shows us, though, is that we get a state rho that lives in a very large dimensional space, this Fock space of whatever. They had 16 different photon numbers, for example. But the actual encoded state, remember, was something that was encoded in the 0 alpha basis. 0 and alpha, two orthogonal states. It was a qubit originally. But it's encoded in a large dimensional state. Yeah, so this is like 0 and alpha, for example. And the question really, well, the problem is that this state here, of course, because it lives in such a large dimension, can have a very large entropy of up to log n plus 1, right? Large dimensional states can have large entropies. And on this side here, this is a qubit state. The maximum entropy of that one is log 2. Or whichever basis of the logarithm. So there's quite a difference in the logarithm of these two numbers. And that's indeed what happened. So what we didn't say in that paper, but what is there, is that in fact the entropy of this state is 1, not 0 as expected. This one was 0, which is what was expected. This one here was also 1, not as 0 as expected. This one here is 1.2, which is okay, as expected. Why is that? Because the coherent state bleeds or leaks into the other dimensions, always. Okay, this is an artificial effect from this alpha state being encoded in a high dimensional space. And the task is, okay, given we know this state and we know how it happened in that sense, I need to put some stuff up. So basically, what happens is that this state, the alpha state, sort of bleeds or leaks into this other space, in this large dimensional space. So this is an assumption we make here, that this is what happens while the zero state stays the zero state. So when you have such a physical situation, the question is, how do you then recover from your known state that you have tomographically found? How do you recover your best bet of a qubit state that you actually know that you should have? How do you do that? And so the problem is that, so the state you have is a large dimensional state, which has, by construction of what I just said, the probabilities in this corner and in this corner are the same ones of your qubit. What's not clear is, how do you take all these coherences on these two sides and put them into coherences in this qubit state? Do you understand what I'm saying? So if you had a classical problem, it would be super easy. You would have, you know, many different possible outcomes, 1, 2, 3, 4, and so on. And all you need to do is, instead of fine-graining your entropy and adding each pj log pj, you actually first add up the probabilities for the whole bunch in this subspace, and then take pb log pb. That's it. You don't have any coherences, you don't have any problems. Now you have coherences. What do you do with them? How do you get the coherences into one coherent? So that's, and what you of course want is that, of course, you expect that your entropy will decrease as a result of your map. And you also want, of course, that whatever best sigma you make, the entropy of your best sigma should never be smaller than your original state. Your original state had an entropy and it only got noisier. So you don't want to sort of artificially lower the entropy. You just want to recover the noisy quantum qubit state. And so this is where I run out of time, and I just tell you the solution. The solution is this. The solution is, there's a particular formula for this coherence C here, and the formula is given by this stuff, which is a highly non-linear expression of the state. So rho is the state, and you have to project it into the subspaces, rotate it, and diagonalize, and then you differentiate, then you divide these two things by each other, take the square root and all that. So the bottom line is, there is a prescription of how to do it. So this is still preliminary work, and the problem is a little bit that the whole operation is highly nonlinear, and therefore it produces some errors. When you apply it to real data, you have some problems, because you put together numbers that you shouldn't put together, because that is not a proper state anymore, and all sorts of things. But so I show you extremely preliminary numbers. This one here, for example, is negative. Shouldn't be negative, okay? But you see, it's roughly right. It's 0, okay? I mean, so it comes from applying a highly nonlinear operation onto actual data that you get such errors. So that needs some numerical issues. But the prescription would work perfectly if it worked on perfectly noisy state, not on some real thing. Okay, and then here, for example, it should be 0. We had 1, now it's 0.1, much better. Okay, this is a realistic thing now. And also here, for example, this should be 1, and we have 0.95, which, you see what I'm doing, right? So we've recovered a qubit state that has reasonable entropies now, which is what we needed back then and didn't know how to do. So I come to the end. We talked about different things. We talked about first this mean force Gibbs state, and how that is actually the steady state, and how different coupling regimes are all present. And that we have a general analytic expression for these two regimes, the recoupling limit and the ultrastrong limit, that applies to all sorts of systems, and it might be useful for what you do. And then in the second part, we talked about this, how to recover from a known noisy state, rho, that you see in your experiment, a qubit state that is actually underneath it. And I showed you some indication of how to do that and how to recover this coherences here with the correct entropy properties. And so I come to the end. So these are the people who really did all the work. So Jim did all the calculations on this mean force corrections. So he's an extremely clever person who's now that he's retired, he can actually do so much more physics than he was probably able to do when he had to do a lot of teaching before. And then these two guys here, we wrote this paper, which you might be interested in. This is number 2. This is about mean force Gibbs state, sort of a review article with all the things to do with that. And these are the experimentalists who did this quantum Maxwell Demon experiment. There were others as well, but I just highlight them. And then I should say, there's a sort of connected talk to what I just talked about, and that talk will be by Federico Cerijola. As I understand it, it's going to be filling the talk later today, the talk slot. That will be after lunch. So Federico will be following up a little bit on this mean force business with much more concrete details. And with this, I thank you very much for your attention.
Thank you, Janet.